Let's look at some adding and subtracting now. So if you look at 7 through 9, we've got some radicals, some exponents in there. So let's just look at number 7 first. Just like when you had square roots, these are fifth roots, and in order to add or subtract them, they have to be the same. So if you're looking at this, what we need to pay attention to is what's attached to the lead coefficient. So just like when you guys have 3xy plus 2xy, you're not going to like add the x and the y, or the x and the x and the y and the y. You're just going to say how many xy's do you have. So you would have 3 xy's plus 2 xy's, so you'd have a total of 5. The same thing goes for these. They look a little weird, but you're only concerned about how many of whatever you're working with you have. So for number 7, you have these fifth roots of 12. Now, there aren't any perfect fifth roots within 12, so you don't have to worry about simplifying those, but how many do you have? If you have 7 fifth root 12s minus 1 fifth root 12s, you've got a total of 6 of them. So that's what I mean. You only add or subtract those lead coefficients, you just keep whatever is attached to them. So if we look at number 2, or number 8, the second one, right now they are both a cubed root, but they're not the cubed root of the same thing. So we're going to have to simplify like we've done in the past and hope that after we do so, they have the same thing underneath that radical. So you can look for perfect cubes or you can break it down. And because it's a cubed root, here's how we're going to have to do this. Before, say you had 12, square root of 12, you guys would find pairs and circle the pairs. The reason you did that is because you were looking for indexes of 2 because they were square roots. So now you guys have to pay attention to what root you're dealing with. So if we're looking at cubed root, what's going to happen is we still want groups, but we want groups of 3 because we need perfect cubes instead of perfect squares. So you'll still break it down like you normally would, but now we want a group of 3 to match our index instead of 2 because it used to be a square root. So that group still comes out. That 3 is still what's left. So it's just 3 cubed root 3. One pair still equals one number out in the front. So let's do 24. So it doesn't matter, 12 and 2, 6 and 4, 8 and 3. You'll still end with the same thing. So it looks like we've got one group of 2's and a 3 left. So we've got 2 on the outside, cubed root of 3. Now it is important that you guys put that index of 3 there, because if you don't put that index there, I'm just going to assume that you think it's a square root because you wrote it as a square root. So make sure you're paying attention and putting the correct index that you're using in there. So now we've got 3 cubed root 3's minus 2 cubed root 3's. So that leaves us with just 1 cubed root of 3. You don't have to write the 1, but you can. So just pay attention to what your index is or your root, and you're just, again, factoring it and finding those groups like we've done in the past. So let's look at number 13. So for this one, we still need to look at the fourth root of the numbers underneath the radical, but now we've got some variables to pay attention to. So let's just take it one piece at a time. So if we look at the first one, 10 times the fourth root of 5s to the 7th. So you can't find any perfect fourth roots within 5. So that 5 is going to just stay underneath that radical. But for the s part, what we need to do is figure out how many times 4 goes into 7. So if you did 7 divided by 4, it would go in one time with 3 remaining, correct? Well, that 1 tells you that we're going to pull s to the first power out, and there's going to be s cubed left. You could also do 7 s's, 1, 2, 3, 4, 5, 6, 7, and you can say, oh, well, there's a group of 4 we can pull out, and then there are also 3 left. So that's sort of how there's 2 ways you guys can do that. It's sort of whichever works best for you. It's just that once you start getting the higher exponents, to really sit there, say you had like s to the 23rd, to sit there and really write out 23 s's is just kind of time consuming. So you're figuring out how many times the index goes into that power underneath the radicals. And then don't forget the 10 that was already out there. So we've got 10s times the 4th root of 5s cubed. We're going to bring down our minus sign, so just always be paying attention to what sign you have. And then we're going to simplify the next part. So 4 doesn't go into 3 at all, so that s cubed is going to stay. And that makes sense because that's what we have in that first term over there that we just did. So s cubed is going to stay, and we can actually wait to do that. So we need to simplify 80. So we can do 10 and 8, 2 and 4, 2 and 2, and 5 and 2. So there. Okay, so we've got a 4th root, which means we need a group of 4 2's, which we just found, so that can come out with the s that's already out there. And it looks to me like this 5 and s cubed are going to be what's left underneath your radical, your 4th root. So the 5 and the s cubed. So what we have here, we're paying attention to the lead coefficient. So it looks chaotic and messy, I get that. But we have 10 s 4th root of 5s cubed minus 2 s 4th root 5s cubed. So that is what is staying. We're still keeping that s times the 4th root of 5s cubed. But how many of them do we have? Well, 10 minus 2, so 8. So it's really just taking it one step at a time. And once you're done simplifying each individual term, you should be able to combine them because they should be the same then. So number 14. Again, lead coefficients are 15 and 8. So is what's attached to them exactly the same? Same variables with the same powers. Yes. A fourth b to the 2/3. How many a fourth times b to the 2/3 do we have? 15 plus 8. So 23 a to the 4th, b to the 2/3. So now the only thing we have to fix, we don't have any negative exponents, but we can't have exponents that are fractions. So we're just going to simply rewrite that in radical form, just the b part. So the cubed root of b squared. So either like that, you can do it like that. Both of them are the same. As long as you don't have an exponent that's still a fraction, you're okay. And no exponents that are negative. So let's look at number 9 yet. Same idea. We can rewrite that 9 to the 2/3 in radical form now, or we can do it at the end. It doesn't matter, but they're actually exactly the same. 4 9 times the 2/3, or to the 2/3 plus another 4 times 9 to the 2/3. But we're paying attention to what is attached to the 4, so we've got 8 of these 9 to the 2/3. And I'm going to rewrite 9 to the 2/3 in radical form. And 9 squared is 81. So I'm going to simplify to make sure I don't have any perfect cube roots underneath here. So we can do 9 and 9, 3 and 3. So because that perfect cube is in there, I'm going to pull that out and make this 8 times 3 times the cube root of just that single 3 that is left. So this becomes 8 times 3, which is 24. So we've got 24 cubed root 3s. So when you're adding and subtracting, even though it seems weird, you guys want to try and make sure that what's attached to that lead coefficient is the same once you're done simplifying, and then say, okay, how many of whatever you're working with do you have? And that's it.